Welcome back to The Explainer. Today, we're diving straight into Chapter 18, focusing all on the spark of chemistry, unlocking electrochemistry. This is that incredible arena where electricity and chemical reactions literally collide. We're going to see how we can actually use electrical energy to just completely rip apart the fundamental building blocks of matter.
So, let's get right into it. Have you ever wondered how exactly electricity can turn something as simple and everyday as water into literal rocket fuel? I mean, how do we transform water into a powerful energy source capable of launching rockets into space or driving the cars of tomorrow? Well, the answer comes down to this microscopic, highly choreographed dance of ions and electrons.
To break down everything in this chapter, we're going to quickly hit the basics of electrolysis, splitting molten compounds, aqueous solutions, and competition, the rules of half equations, electroplating metals, and finally, wrap it up with a hydrogen fuel future.
Part 1. The basics of electrolysis, or the rules of the game. Okay, the big word we're tackling first is electrolysis. Now, if you break down the root words, electro obviously means electricity, and lysis means to split or break apart. So electrolysis is basically just using electrical power as a tool, kind of like a microscopic crowbar, to force a chemical compound to decompose. But there is a catch here. The compound actually has to be melted down into a liquid or dissolved in an aqueous solution, just so its internal components are free to move around.
Right, so let's picture the actual setup of an electrolytic cell. You've got a power supply at the top, and you can think of it acting almost like a bouncer at a club, right? It's forcing electrons to move in one strict, orderly direction through the external wiring. Then you have these rods dipping into the liquid. Those are the electrodes. The liquid itself is our electrolyte. That's where those dissolved or molten ions are just hanging out, waiting for the electric current to give them a push.
Now, in this system, it's absolutely crucial to remember that opposites attract. It's basically a giant electrical tug-of-war. The anode is our positive electrode, so it naturally pulls in the negatively charged ions, which we call anions, and oxidation happens right there. The cathode, on the other hand, is the negative electrode. It's drawing in the positively charged ions, the cations, which is where reduction takes place. It's this perfectly polarized setup that separates out the chemical mixture based purely on electric charge.
Moving on to Part 2, splitting molten compounds through molten electrolysis. This is where the chemistry gets really wild. Think about the electrolysis of molten lead bromide. Because we've completely melted it down, the lead and bromide ions are totally free to travel. So the positively charged lead ions just rush over to the negative cathode. There they pick up electrons and physically pool together as liquid lead metal. At the exact same time, the negative bromide ions race off in the opposite direction to the positive anode. They drop off their extra electrons and just bubble away into the air as this reddish-brown bromine gas. We are quite literally tearing a single compound into its two pure elements.
Part 3. Aqueous solutions and competition. Let's see what happens when we add water to the mix.
Okay, but what if we don't want to use massive, intense amounts of heat to melt our chemicals? Well, scientists use this brilliantly designed piece of glassware known as a Hofmann voltameter. It perfectly captures what goes down when we run electricity through water that just has a little bit of acid mixed in to help conduct the current. Because water is made of hydrogen and oxygen, the electricity actually splits it apart. Inside the tubes, the negative cathode grabs hydrogen gas and the positive anode grabs oxygen gas. And because water is H2O, you get this beautiful, perfect 2-to-1 ratio of hydrogen to oxygen bubbling up.
But things get a bit spicy when we dissolve salts in that water, because a competition begins. See, water naturally has a few positive hydrogen ions and negative hydroxide ions just floating around. And these are going to directly compete with our dissolved salts ions to see who actually gets discharged at the electrodes. The rules for this microscopic competition are super strict. At the cathode, the least reactive positive ion always wins. Always. So if you've got a highly reactive metal like sodium competing with hydrogen, hydrogen wins the fight and bubbles off. At the anode, if you have a really high concentration of a halogen like chloride, it's going to beat the hydroxide and form chlorine gas.
Now, what's really fascinating here is how clearly this competition plays out. Let's take regular old sodium chloride, table salt. If you melt it down with extreme heat, the only things in there are sodium and chlorine. So at the cathode, you just get pure sodium metal. Boom! But the second you dissolve that exact same salt in water to make a concentrated aqueous solution, the entire game changes. Water's hydrogen jumps into the ring, completely beats out the highly reactive sodium, and suddenly you're producing hydrogen gas at the cathode instead of sodium metal.
It just goes to show context is literally everything in chemistry.
All right, part 4, the rules of half equations and how we actually track those electrons.
To really understand the math of what's happening in Chapter 18, we use half reactions to track the electron exchange. And the fundamental rules here are all about oxidation and reduction. Oxidation is the loss of electrons, which always happens at the positive anode, where negative ions go to drop off their baggage. Reduction is the gain of electrons, happening at the negative cathode, where positive ions arrive to pick up some electrons. You add these half reactions together to find the overall equation. They're the vital bridge that completes our electrical circuit. Just remember, the electrons themselves are moving through the solid wires, but it's the physical ions that are moving through the liquid electrolyte to keep that current flowing.
Moving to Part 5, electroplating metals and taking this to industrial applications.
This process brilliantly illustrates the industrial power of what we've been talking about. Think about the electrolysis of a blue copper-2 sulfate solution. The negative electrode, the cathode, literally gets coated in a solid red-brown layer of pure copper metal. This isn't just some neat lab trick. We use this exact scientific principle industrially to plate silver onto fancy cutlery or to slap a shiny rust-proof layer of chromium onto motorcycle parts and car bumpers. We are essentially painting with metal, using electricity as the brush.
And finally, Part 6, the hydrogen fuel future and clean energy solutions.
So if we want a seriously powerful fuel for the future, we have to look closely at energy density. And hydrogen vastly outperforms traditional fossil fuels here. It pumps out a massive 143 kilojoules of energy per gram, absolutely dwarfing things like methane and standard petrol, which are way down in the 50s and 40s. It produces way more energy per gram than literally any other fuel, which is exactly why NASA uses it in rockets. But the big question is, how do we harness it for everyday life down here on Earth?
Well, all this science builds into an absolutely incredible piece of technology, the fuel cell. A fuel cell essentially just runs the electrolysis process we've been talking about, but in reverse. So instead of using electricity to split water into hydrogen and oxygen, a fuel cell takes hydrogen gas from a tank, pulls oxygen out of the ambient air, and forces them to combine. This chemical reaction continuously generates an electric current that can drive a motor. And honestly, the best part? The only exhaust product created when hydrogen and oxygen combine is just pure, clean water. No smog, no carbon.
To tie this abstract chemistry directly to our reality, we can look at the actual vehicles using this today. We've got hydrogen fuel cell ecobuses currently operating on city streets and sleek, modern, hydrogen-powered consumer cars. This is not some far-off science fiction. This is the real-world payoff of understanding ion transfer and electrochemistry. These vehicles are out there right now running on the exact principles we've just outlined, driving silently with absolutely zero greenhouse gas emissions.
But, as with everything in science, we've got to be objective and look at the whole picture. The advantages are undeniably massive. If we use renewable energy to make the hydrogen in the first place, the whole life cycle is virtually emission-free and non-toxic. However, the logistical challenges are very real. Hydrogen gas has a super low density, which means these cars require large, high-pressure fuel tanks. Plus, right now, there are very few filling stations, and the technology to safely store and transport the fuel at scale is still quite expensive.
Which brings us to this really powerful takeaway from Chapter 18. The ultimate goal isn't just to make hydrogen, it's to make green hydrogen. Right now, a lot of industrial hydrogen is actually produced using fossil fuels, which kind of defeats the whole purpose, right? But if we can harness cheap surplus electricity from massive solar or wind farms and use that clean electricity to perform the electrolysis of water on a massive global scale, well, then we can generate the clean fuel necessary to act as a true pillar of a completely decarbonized economy.
So we started this explainer looking at a simple battery splitting water in a lab, and we've ended up at the literal frontier of global energy solutions. I want to leave you with this thought to chew on. As technology rapidly advancing, driving down costs, and building better infrastructure, will this green hydrogen economy be the ultimate key to solving our climate crisis? It's a massive question, and the answer relies entirely on the fascinating science of electrochemistry. Thanks for hanging out and exploring this chapter with me today. Keep asking questions, and I'll catch you in the next one.